Okay, so welcome. Today is Friday, January the 8th. Okay, and we're at AP Chemistry here at Spain Park High School. So today we're going to be talking about enthalpy. So we went over those problems in the textbook. Well, I assigned them for you to do. Okay. Would anybody bet me a nickel you got them right? I'm not hearing anything. So the first one was on page 206. It was number 43, right? No. Those are what we did in class. We were doing on 208, number 74 and 75. So let's get those up. For those of you at home, again, we're going to be doing a lab on Monday and Tuesday dealing with what we're going to learn today, Hess's Law. And so you need to come prepared for lab. I'll try to put out a remind as well on that. But long pants, closed-toe shoes, hopefully, I mean, it's been so cold, long pants is pretty obvious. Okay? So if we look at number 74, okay? You're going to have to go to Appendix C in order to be able to get the values for the delta H of formation for each of these. That's page 1100 in your textbook, okay? So, but on the AP test, that's just going to be given to you, okay? That's going to be just somehow given within the problem, the values for delta HF. But when the key equation, delta H of a reaction, and what does that degree symbol mean? Say that again? Standard conditions. And what are standard conditions for everything but a gas? 1 atm at what temperature? 25 degrees Celsius, not 0. For gases, it's 0. For everything else, it's 25. So the delta H of the reaction is the sum of the heat of formation of products minus the sum of the heat of formation of reactants. Now, I only looked, a few people yesterday had submitted the answers to these problems ahead of time, and 2 out of the 3 did that backwards. They did reactants minus products. So we have to really make sure you do that products minus reactants. This equation is given on the equation sheet for the AP test, okay? So you just have to go and you have to look these up. So what did you find for the heat of formation of calcium chloride? I'm going to need y'all's values, so I don't want to look that up on the chart. It's going to be 1 mole times, what is the value for calcium chloride?
Negative 795.
Negative 795.8, and that's kilojoules per mole. Plus water, it's 1 mole, negative 242 point.
Negative
.8. Okay. Yeah. Minus the products, which is going to be 1 mole times, what's the heat of formation of CaO? Negative 625?
35.
Negative 635? Okay, plus, let me mute this, the last one is HCl, but we have 2 of them. So it's going to be plus 2 moles times the heat of formation of the HCl, which was negative 92.3. Okay, so it's really just plugging into this formula. That's all you got to do. Okay, so these values again are all given. The only thing you have to know is that this is kilojoules per mole. So if we're making 2 moles of it, whatever the coefficient is, we got to multiply by the coefficient. Moles all cancel. So that leaves us, what value, what number?
-217.52
.552 kilojoules. Okay, what does the negative sign mean? That it's an exothermic reaction, energy is released. Okay, so what's going to happen to the reaction vessel that this reaction is taking place in? It gets hotter. Because that energy is released to the surroundings. So the system has less energy, but the surroundings absorb that energy and get hot. Okay? I heard someone say, oh, it's a gas. You have to pay attention to the states. The water is, you got both liquid and a gas. Some of the energy is used to convert from a liquid to a gas, so the heat of formation of a gas is less than the heat of formation of a liquid. So you gotta pay close attention to the states for these things, because that would be a common mistake. Now, I would think that on the AP test, they would just give you the heat of formation of the gas or the liquid, whatever state it was in, and not give you both, but you never know. Okay, so this was 74A. D is gonna be the exact same setup. So what did we get as an answer for delta H of the reaction for D? Just the answer.
-196.1.
-196.1. Do we agree on that? Did other people get that? Do I need to go over this one as far as where the values came from for anybody? Okay, so we're all comfortable. It's gonna be the exact same format, just multiplying coefficients times the heat of formation, okay? Moles times heat of formation, and then just add them up. Okay? So, that's pretty straightforward. We like this equation. We like these type of problems. They're relatively easy. Now 75, complete combustion of 1 mole of acetone liberates this much energy. What does the word liberates mean? Okay, so somebody in the back, what'd you say? It's exothermic. It releases, liberates, frees that much energy. Okay, so that's a word that sometimes confuses students in the past, that it liberates the energy. Okay, so we know now that delta H is going to be the -1790. So that's important. That may not have been given in a problem. It may just give it in the words, and you need to know that that translates to this here. Now, if I was going to write it into the equation, where would I put the 1790? On the product side. Okay? If it was positive 1790, we write it on the reactant side. All right? So we just need to understand those basics. So using this information with the standard enthalpies of formation from Appendix C, calculate the standard enthalpy of formation of acetone. So how is this problem different than the one we just did? Say what? You don't know one of the reactants. But I do know what the final answer is. So this time, and if you need to move that, delta H of the reaction is equal to -1790, is equal to the sum of the heat of formation of products, which is going to be 3 times -393.5. I'm going to save space in units. Plus, what's the 3 times 285.8? Okay, plus, this is my 1 mole, but this is my X, the delta H of formation of the C3H6O, plus 4 times, what's the heat of formation of oxygen? 0. Why? It's an element. The heat of formation of elements is always 0. You can't form an element, it's already made. Okay, so it's just going to be 4 times 0.
over here in the middle, or subtract.
Oh, God. Thank you. I'm telling you what, I'm really starting to worry about my brain. It's starting to really, I think the bread's beginning to mold. I'm making all these kind of stupid mistakes. I mean, I just said the products minus reactants and I wrote plus. Okay, so now we just have to solve, really, this is X. Okay, that's just your unknown. So you just got to do the algebra and solve for X. So it's really minus X because that term is 0. So you just go through and solve. So the heat of formation of delta H of C3H6O. What's the answer come out to?
Negative 248.
Negative 248. And that's going to come out to kilojoules per mole. Because we're going to have, this is kilojoules, that's 0. The answer over here is kilojoules. But so you're going to collect all the like terms and you're going to subtract, you're going to have kilojoules. But then you're going to have to divide by 1 mole. Now, if there happened to be a 2 or a 3 or a 4 there, you'd have to have that there. Okay? Because you always multiply by the coefficient. It just happens to be a 1. But that's where the per mole comes from when you divide by that 1 mole. So for this is the third way we can calculate delta H, is just products minus reactants. The numbers are all given. These are the only two only two types of these problems. Is either you're going to solve for delta H, or you're given delta H, have to solve for one of the heats of formation. Equations given, all the values are given. It's a relatively straightforward problem. Which then takes us to the next one, which is not quite as straightforward. Hess's law. Now Hess's law says that if the equations add together, then the heats add together. The heats of formation, the heats of reaction are summative. If the equations add up, then the heats are going to add up. So again, who remembers what I said a state function is? That enthalpy is a state function.
Like it doesn't matter, like the path you take, the answer's always the same.
That's exactly right. Doesn't matter the path you take. And I use the example, if you drive from here to Denver, there's a bunch of different routes you can take and the mileage would all be different. So the path matters as far as the overall distance. However, if you're just measuring the change in altitude from here to Denver, no matter what path you take, the change in altitude is going to be the same. So that would be a state function. So calculating enthalpy is a state function. It doesn't matter what path you can take. You can do 2, 3, 4 different equations to get to the final one, or you can do it all in one step. The delta H is going to be the same. That's what Hess's law says. Okay, so if you're looking in the notes that I just gave to you, and I'll get you a copy at the break. Okay. We are now, well, do they give Hess's law? Yes, it's starting on page like 8. Okay, so they kind of combined this Big Mama equation. I don't know where they came up with it. This is National Math and Science Initiative. They came up with all these notes and they're way prettier than anything I could put together, so I just stole them. But if we look, and by the way, we need, if the weather's been so bad, we're going to do this thermite reaction that is given an example on the page 8. We're going to go outside and do that, and it's really, I say it's really cool, but it's really very hot. It generates a tremendous amount of heat. It's fun to watch. So as soon as it's not raining and it's maybe not like freezing cold, we'll go outside and do that one. But if we go down and we look at exercise 11 on page 8, it says calculate delta H for this overall reaction. So they give the overall reaction. I guess I'll just put this up again. So this is what we want to get the delta H of the reaction for. But for some reason, we don't have the heats of formation, we don't have, you know, all the information, but we have these individual reactions. But if we can make these three add up to that one, then the heats are going to add up to that one. Okay? Now there's going to be, we can reverse the equation, we can multiply the equation, and we can just put them in any order and add them. Okay? Now what do you think, since the heat of formation is products minus reactants, if I reverse the equation, what's going to happen to the sign of delta H? It's just going to change, right? It's going to go the opposite. 3 minus 2 is equal to positive 1. 2 minus 3 is equal to negative 1. You get the same number, just opposite sign. So if we switch an equation, we're going to change the sign. If we multiply an equation, because it's a, well, I'm trying to think of the word. It depends upon the amount of substance that's present. It's a physical property, but there's two types of physical properties. In my mind's again, I'm worried about my brain here. What are the two? One that depends upon the amount of substance and one that doesn't depend upon the amount of substance. Extensive, that's the word I was thinking. Intensive and extensive. It's an extensive property. Thank you very much. An extensive property. So as a result, if you multiply by 2, you got to multiply this by 2. If you multiply this by a half, you multiply this by a half. Okay? So, the way I try to do this is I try to look, now H3BO3 is only here. That's the only place H3BO3 is, right? So I know that it needs to stay on the left-hand side, but I need 2 of them. So I'm going to multiply this equation by 2. Which means, and look, the delta H is huge here on this. I have to multiply this whole thing by 2. All I'm trying to do is make these 3 equations add up to this one. So I'm just going to start on the left, and I'm going to find the different components and find out what I need to do to get that. So the next component I'm going to look at is the B2O3. Well, where is B2O3?
Third one.
The third one, right? And it's already on the right-hand side, so it's in the correct position, but I have 2 of them. How many do I need? 1. I only need 1. So I have to multiply this by a half. So I have to multiply this one by a half. Now, I have H2O liquid. Where's H2O liquid? In all 3 of them, right? But I need to get some things to cancel out. So I know that I have H2B4O7 on the left, that I don't need it anywhere in my equation. So this H2B4O7 right here, I'm going to have to put on this other side and multiply it by a half in order to be able to get to where I need to go. Because this is only going to be a half H2B4O here, so I need a half H2B4O7 on the other side to cancel it out. Right? So I'm going to need to reverse this equation and multiply it by a half. Now I'm going to go ahead and rewrite that one as 2HbO2 plus, no, not plus, goes to 1/2 H2B4O7 plus 1/2 H2O. So what do I have to do to this? I got to multiply it by a negative 1/2. And I got to change the sign. I'm going to change it to positive and multiply by a half. So my 3 equations then are going to be this one, and then it's going to be 2 H3BO3s going to 2 HbO2 plus 2 H2Os. And then this one is going to be 1/2 H2B4O7 goes to B2O3 plus 1/2 H2O. So this is the three equations that I'm gonna net out after I do all of my changes. So now you can see the two HbO2s are gonna cancel out right there. The 1/2 Hb4 is gonna cancel with the 1/2 H2B4. So we're left with H3, two H3BO3s goes to B2O3 plus 2 plus 1/2 plus 1/2, 3 H2Os. So now I can say, okay, so this is gonna equal negative 0.04. This one's gonna equal a positive, what, 5.65? Is that what that equals? Nobody's helping me out here with the math, but I think that's right. Yes, sir.
So why would it be negative to change it?
Because we flipped the equation, we reversed the equation. So delta H is equal to products minus reactants. So when you switch it, the reactants become products and the products become reactants. And so you're just gonna change the sign. Again, 3 minus 2 is 1, 2 minus 3 is -1. They're same number, just opposite sign when you reverse it. And then this one is gonna equal, half of this is gonna equal 8.75. And that's gonna be positive. And so we add all that together, and what do we get?
14.36.
14.36. I like two decimal places on this because we have two, no, we only have, well, that's true, because on this one, when you divide, you only have one decimal place, so you really should only have one decimal place here. Although when you divide, you have 3 sig figs. I go with 14.36. And that's going to be kilojoules. And it's gonna be, what they give in here, they'll give a per mole reaction. Notice this per reaction. In other words, and this is a made-up unit that AP just made up about 5 years ago, that just says, okay, so this is the heat per this reaction, per a mole of this reaction. But it's still, you're gonna have to multiply. If they wanted to know per mole of this, you're still gonna have to know and divide by 2 to get moles of that. So this is kind of like an algebra with a series of equations that you're just gonna have to add together. And we're just trying to get certain things to cancel out and other things to add up. And I always just kind of go right down the line. Start with this one, find out where this one is. Notice the water's in all of them. So I'm gonna leave water to last because I just gotta let it work itself out. Find the things that are only in one place and get them in the right place with the right amount. So you can manipulate the equations, you can multiply by 2, you can multiply by 1/2, you can reverse equations to get things to the other side. But whatever you do to the equation, you have to do to the delta H. But Hess's law, since it's a state function, it doesn't matter what path you take. If you can get to the same final answer, the delta H's is gonna be the same. But the delta H's are added to summative, is what Hess's law really says. So, where did I just put down? I made a bunch of copies. Some practice on Hess's law. This is yours, so you can write all over it. So take a second and look at number 36 and see what you can do with number 36. All right. Yeah, I know, it's just that's just from the light coming from the camera. I can't, absolutely nothing I can do on that one. Okay, so, where do I wanna start? If this is the equation I wanna find delta H for, which equation do I start with? You can start with any of them, but I always like to just work left to right on this one. So since I have carbon is the only place here, the only place carbon solid is right here. So I'm gonna start with this equation here, and I'm just gonna multiply it by 2 to get my, it's already in the right place, so I'm gonna say 2 times carbon solid plus 2 O2s goes to CO2 gas. And then delta H, since I multiplied it by 2, what do I have to do to delta H?
Times 2.
It's gonna be 2 times negative 394,
Isn't it two C?
and it'd be 2 CO2. So that comes out to equal 788.
Yeah.
So then, H2 gas. H2 gas is only right here. O2, notice O2 is in every place. H2 is only right here. I have a H2, I have H2, so I don't have to do anything to this equation. So I can simply say H2 gas plus 1/2 O2 gas goes to H2O liquid. So delta H just stays exactly what we had, which is negative 286. So now I need to find the C2H2. C2H2 is here. I need it on the right-hand side of the equation. I need it as a product, so I'm gonna have to flip this, okay? I only need one, and I have one, so all I have to do is reverse this equation. So I'm gonna end up with 2 CO2s plus 2 H2O goes to C2H2 plus, what is that? 5 halves O2 gas. Okay, so what do I do to my delta H?
Negative.
Just change the sign, right? So it's gonna be negative 1300, it's gonna be positive 1300. So we just double check to make sure that everything cancels out. I have 2 carbons, I want that to stay. I have 2, 2.5, my 5 halves of oxygens cancel out right there. 2 CO2s cancel out right there. My H2Os cancel out right there. So now I'm just left with 2 carbon solids plus H2 gas yields C2H2 gas. So my delta H is going to be the sum of 1300, negative 286, negative 788. So delta H equals 226, positive 226 kilojoules. And again, they're gonna say per mole reaction, but it's really just kilojoules. Is everybody comfortable with that? Okay? Let's try probably one of the most challenging ones, just to give you a little bit of a challenge here on a Friday. Let's go up to the one at the top. To this one. I'll just give you a clue. You got a lot of fractions. You got to know how to do your fractions on this one.
34 and
34. 34. So let's look at this. What do we do? Make sure that I'm in the frame here.
You start with FeO.
Okay, I want to start with FeO because that's the one here, and it's only in one place. The only place FeO is right there. Okay, so what do I need to do to this equation? Reverse it and
1/3.
multiply by a third. So I'm gonna reverse it, and I'm gonna say FeO plus 1/3 CO2 goes to 1/3 Fe3O4 plus 1/3 CO. So what do I do to my delta H?
Negative 1/3 times that.
So delta H is equal to negative 1/3 times 38. Right? Negative 1/3 times 38, which is gonna equal negative 12.67. Is that right? Okay? Now which one can we do?
Do the first one.
Well, see, CO is in all of them, right? CO2 is in all of them, so I wanna leave those, so I wanna just do my Fe solid. Okay, because it's only in one place. So I'm gonna get confused if I'm trying to do the ones that are in multiple places. So my Fe solid is only in the first equation. But I only need one and I have two, so I just have to multiply that first equation by a half. So it's 1/2 Fe2O3 plus 3/2 CO. This is where you gotta remember your third grade fraction rules. Okay, goes to Fe solid plus 3/2 CO2. So again, my delta H is gonna equal 1/2 times the given value of negative 28. I can do this math pretty easily, is equal to negative 14. All right, so now it really gets tricky. So we have to say, okay, I gotta get only a CO on the left and a CO2 on the right. Well, right now, I have 3/2 and 1/3 CO. That's not gonna cancel and make me 1. Do I need more or less?
What?
Less.
Less, right? Which means the CO is gonna have to go onto the right-hand side. Okay, does everybody follow me on that? The logic on how I'm figuring this out? Okay, so the CO has to go on that. They only have one more equation. I only have, this equation left to mess with. I also know that Fe2O3 has to cancel out. So the Fe2O3 has to go on the other side. And I have 1/2 Fe2CO3, so I have to multiply this by what to get 1/2?
1/6.
1/6. So I'm gonna have to multiply by 1/6 and reverse it. So that's gonna give me 1/6 times 2
1/3.
is 2/6, which is 1/3. 1/3 Fe3O4. Which, looky there, I have 1/3 Fe3O4. Plus 1/6 CO2. Goes to
1/2.
3/6 or 1/2 Fe2O3 plus 1/6 CO. All right, so now I reversed, so delta H is gonna equal negative 1/6 times negative 59. That's gonna come out close to 10, but what does it come out to?
9.83.
9.83. But we have to verify that everything's gonna cancel. FeO stays. 1/3 CO2 and 1/6 CO2 is equal to 1/3 and 1/6. If we change this to 6, this is 1/3 is 2/6 plus 1/6 equals 3/6, so it's gonna be 1/2 CO2. All right? Then I have 3/2 CO2 here. Okay? So I have 1/2 and 3/2, so I'm gonna end up with just a CO2 over there. Right? So that's my CO2s are all now accounted for. My COs, it's gonna be basically the same thing on the other side. 1/3 and 1/6 makes 1/2, you have 3/2, so you're just gonna get the 1 CO on this side. 1/2 Fe2O3, 1/2 Fe2O3, 1/3 Fe3O4, 1/3 Fe3O4. My COs I've already taken care of. So that leaves me FeO solid plus CO goes to Fe solid plus CO2. So my delta H is gonna equal -12, so -26 plus 9, what does that all come out to?
16.8.
-16.8? Good job, that was hard. Hard with all the fractions, but the key thing that I want you to see is once you get the 2, figure out just which one do I need to cancel out so I know which side it goes to. Just pick one thing that has to change, make it work, everything else will work out. Okay? All right, so. Here's an old AP problem. I'm not quite sure what year this is. But I just kind of want to show you how a Hess's law can get worded in this. Oh, that's not yours. Okay, so it says, we're only gonna look at 3, A, B, and C here on this. But 3 says, calculate the standard enthalpy change of delta H for the reaction represented by the equation above. Now, what did we say was the definition of the formation reaction? The delta H of formation, what is that a measure of the energy? It's important to know that. That's going to be key in answering A. What does delta H of formation mean?
Products minus react.
Well, that's heat of reaction.
Yeah.
And we use the heat of formations, but when we're calculating the heat of formation, what are we really calculating? When we say the heat of formation of water is -285.8 kilojoules, what does that mean?
Like the energy needed for the elements to combine, or is it?
It's the energy change, positive or negative, energy gained or lost, when elements in their natural state combine to make a compound. So it's a compound formed from its elements. So here, hydrogen and oxygen are combining together to make water. Water is being formed from the elements, okay? But this is kilojoules per how much? Per 1 mole of water. Well, in this reaction, how many moles of water are being formed? 2. If we did products minus reactants, which we could do to calculate the delta H on this, we would just multiply 2 times this, products, minus what? 0. So the answer to this one is pretty straightforward, as long as you understand that the heat of formation, in this particular reaction, the heat of formation is the heat of reaction. It's in kilojoules per 1 mole, so we just gotta multiply it by 2 to get kilojoules per 2 moles. So that's just a formation question. Now look at B. See if you can do B now. B is like the problems that were assigned for homework last night. I'll give you clues. Start with what's given, find the appropriate conversion factor or factors, set your units up so they cancel. So if we start with 10 grams, the question is asking for the amount of heat. So what's going to be my conversion factor for the amount of heat in kilojoules? What did we say was the conversion? This is your first type of way to calculate enthalpy is with stoichiometry. What's the conversion factor? Kilojoules per mole. This. Now this is kilojoules per 1 mole. This is 2 moles. So 1 mole is H2 plus 1/2 O2 yields H2O liquid. That's the one where delta H is equal to negative, that's a delta H of formation, negative 285.8 kilojoules per mole. Okay? So that's my conversion factor. For every 1 mole of hydrogen that burns, it's going to release this much energy, assuming there's enough oxygen. Okay? Kilojoules per mole is your conversion factor between heat and moles. So I have 10 grams of hydrogen. In order to be able to use this conversion factor, what do I have to do with the grams of hydrogen? Convert it to moles using the molar mass, 1 mole over 2.02 grams. Now I can use my negative 285.8 kilojoules over 1 mole. And all that comes out to basically 5 times 285, which is
1,414.85.
1,414?
Yes.
Point 85 kilojoules, but now let's talk sig figs. That would really be, how many sig figs should we have? How many? 3. So what would that be to 3 sig figs? 1410, right? It's not gonna be 141 because 1,414 doesn't round off to 141. 1410 kilojoules. And it's negative. Okay, so that's our stoichiometry type problem for delta H. This is just, do you know what heat of formation is problem. Here, given the molar enthalpy of vaporization, what is the delta H of vaporization? We talked about that at the very beginning of this unit. What is delta H of vaporization? What's the 44 kilojoules per mole? What's that the energy needed to do? Just think of the definition, delta H of vaporization.
Turn into a gas.
The amount of energy it takes to make a mole of liquid change into a gas. So the equation, I need 2 H2O gases. Okay, so I know that I have H2O liquid going to H2O gas. That's what we just said. But in this equation, I need 2 water. So I would have multiplied this equation by 2. So then my delta H over here is going to equal positive 88 kilojoules. Then I know that I have to get the 2 waters to cancel out, so I use this equation that we just figured out and say that, H2O liquid, oh, the liquid's got to go, well, it is on the right-hand side. Did I do it backwards on the last one? It's going to come out different. Anyway, let's see, 2H2 gas plus O2 gas goes to 2H2O liquid. So the delta H of this one, and this is going to be the right answer, 71.6 kilojoules. I don't know what we did on the last one to make it not work, but then I'll cancel out. 2 H2Os cancel out. So I'm left now 2 H2 gas plus O2 gas, 2 H2O gas. So the reality is that 88 kilojoules is not, this isn't what's being added in, it takes that much more energy to make it into a gas, so the overall energy released is going to be less, so it's going to come out to 4 and something. And then we need to go back, somebody go back and look at the way I solved it the last time and see what the mistake was.
We split the sign for the 285.8 when we kept it.
We kept it the same way, we flipped the sign. Okay? I'm telling you, you're gonna have to be watching me here, because I've been making all kinds of boneheaded mistakes. So, what does this come out to? Reagan, you put it in.
483.6, so negative 483.6.
Okay? So this is the right answer. So on the other one, if you want to go correct the other way in your notes, what we did wrong was we changed the sign of the 285 to a positive. It needed to stay negative. So then when you added the delta H's, they were opposite signs. You still multiply by 2 at the end, just got a different value because we made that one small sign error. But notice, this doesn't give it to you in the normal, the reason why I wanted to do this one is it doesn't give it to you in the normal Hess's law, give the equations, what's the overall equation of this one. Sometimes they do it that way, but this one, so to solve it, just write out. But we need to know that the heat of vaporization is the energy it takes to change a liquid into a gas. What do we call it to change a solid into a liquid? Heat of what? Fusion. Okay, the heat of fusion is solid to a liquid. So in other words, to melt ice. So you can do the same thing. So it's just taking the liquid to a gas or the solid to a liquid. That's what your delta H of vaporization. So we need to know what each of these things are: the heat of formation, the heat of vaporization, the heat of the reaction. Sometimes they'll call it heat of combustion, which means it'll be a combustion reaction, heat of neutralization. Just gotta get what all those things mean in your brain. All right, that's the fourth way. Now we're gonna, the fifth and final way to calculate delta H. The fifth and final way. We're actually now going to take a flashback to the past. We're going to go back to chapter 6 on bonding, okay? And bond energies. And if you recall, we skipped over a section of it when it talked about the bond energies, because chapter 6 comes after chapter 5, so they had already, introduced this concept. So we're going to be able to say, this is number 5, fifth way to calculate delta H is going to be the delta H of a reaction is equal to the sum of the bond energies broken minus the sum of bond energies formed.
This is on page 9, that's crazy.
So, if we look at that exercise 12 on page 9, okay, it says that hydrogen plus fluorine makes hydrogen gas plus fluorine gas makes 2 hydrogen fluoride gases. In order for this reaction to occur, these two hydrogen, this hydrogen molecule and this fluorine molecule, those bonds have to be broken, so then the H and the F's can combine with one another. So it always takes energy to break a bond. Breaking up is always hard to do, okay? They write songs about it, they cry about it, breaking up is always hard to do. I think we should just be friends. I hated that speech. Anyway, breaking up always requires energy. Bonds forming is when the energy and the sparks fly, the energy is released. Okay? So we're going to be talking about how much energy does it require to break the bonds versus how much energy is released when those bonds come back and form. Whichever one is bigger is going to determine the overall sign of the delta H. So they give you in this one the delta H of the reaction. In the problem, they give you the bond energy of hydrogen. Well, that bond energy is equal to what?
432.
You guys mumble too much. 432. But we only have one bond, so it's going to be 1 mole times 432 kilojoules per mole. Plus the fluorine bond energy, and we still only have one of them, 1 mole times 154 kilojoules per mole. Okay, that's the bonds broken minus bonds formed. This time we're going to have 2 HF bonds forming. So it's going to be 2 moles times 565. So then you just add that up. What do we get?
Negative 544 kg.
Negative 5 what?
544.
And moles all cancel, so it's just kilojoules. Alright, so that's easy when it's just like this, but let's look at one that's not quite so easy. I'm gonna put the glasses on. It's actually the end of chapter 8. Turn in your books that are right there to page 337. And let's look at number 69.
Well, 337. The page. 337.
337.
The page.
Now notice that the Lewis dot structures are given on this one. Okay? Because we have to know how many bonds are being broken and how many bonds are being formed. Now in addition to this, you're going to need in chapter 8, somebody keep open, turn back a few pages, and they have a table of bond energies in chapter 8. Let's go.
Where's that?
Page 326. Okay? Gives you all of the bond energies. Again, you're never going to have to memorize those. These will always be given generally within the problem itself. But in a textbook, they just give you the charts and the appendixes in the back that you use. But in an AP problem, it's just given within the problem. But when we go and look here, we have to look at all the different bonds that are being broken. So in A, how many carbon to hydrogen bonds are being broken? 4, right? Plus 1 carbon to carbon double bond. Okay? Plus 2 OH bonds. Plus 1 oxygen to oxygen single bond, which, anybody remember, what do we call an oxygen to oxygen single bond? It's a special name, and when it's an O2 with a -2 charge. Oxygen does not like to bond like this. Does anybody know H2O2? What's the name of H2O2? Hydrogen peroxide. This is the peroxide ion right here. Now, you don't need to know that to solve this problem, but I'm just kind of throwing that out just for fun. Okay, so this is all of the bonds broken. Okay, so what are bonds formed going to be? Well, we have 1, 2, 3, 4 carbon to hydrogen bonds again, plus 1 carbon to carbon single bond, plus 2 carbon to oxygen single bonds, plus 2 OH bonds. These are bonds formed. So it's just gonna be, then you just go and you look at the tables and you plug in the values. Now we can do it, I generally don't do this, but on this one it's pretty obvious. You can just do some canceling, since we know it's gonna be bonds broken minus bonds formed, anything that's the same can be canceled. So we can cancel this one out, not even have to figure it in, because they're just gonna, and the two OHs are just gonna cancel each other out. So it's really gonna be this plus this minus this plus that. So the delta H of the reaction is equal to 1 mole, what's the bond, carbon-carbon double bond on the 823? 614. Plus 1 of the peroxide bonds,
146.
146. Okay, so that's broken, minus formed, 1 carbon to carbon, 348, plus 2 carbon to oxygen, 358. So we end up getting this. So then we just solve for it.
Negative 304.
Negative 304 kilojoules. Okay? So that's an approximation. This is not going to be a super accurate, but it's a good approximation of the amount of energy that's going to be released in this chemical reaction. But notice you have to know the Lewis structure. You have to know what's bonded to what and how many of each bonds that we have. The values are going to be given. Now again, the only variable in that is that they can give you the heat of reaction and ask you to calculate the bond energy of one of the bonds. So again, just like on the previous one with the heat of formation, you just know this value and one of these becomes your X. Okay, you still multiply by however many bonds of those there are, but you just kind of look at which one are you looking for. So that's the only two ways to vary this one. So this is, anytime you see bond energies given, it's always going to be broken minus formed. Now this equation is not on the AP. I don't know why they don't include this on the equation sheet. This is one I would program into my fancy calculator that I had with me on the AP test, okay? Which you're allowed to have, and they don't clear the memory. So it's they know that it's there. It's not a matter of memorizing equations. It's a matter of knowing how to use them. Okay? But this one broken is reactants minus products, whereas the delta H and all the other equations that we're going to use are going to be products minus reactants. So this one's kind of opposite of that, but it's broken minus formed. So go ahead then and just do B as practice. Now, you don't have to go through this broken form step. I just kind of did that to kind of show everything. You can go straight to this if you want. Are we finished? Yep. Looks like most of y'all are. Okay, so what we're gonna do is we have, again, delta H of the reaction. I'm gonna use purple. Delta H of the reaction is gonna equal the sum of bonds broken. Well, again, I'm gonna have to break 4 carbon to hydrogen bonds. So what is the bond energy of carbon to hydrogen? 413. And I'm just gonna save space and not use units, but you saw how the units cancel out. I have 1 carbon to carbon double bond, 642, 614, okay? Plus 1 carbon to hydrogen, another carbon to hydrogen, so that's really 5. So I'm just gonna change that to a 5. You could put another one over here if you wanted to, but it's plus 1 carbon to nitrogen triple bond.
891.
891. Look how high that is because of that triple bond. Okay? So that's your bonds broken. It's the sum of bonds broken. Right? Now we do bonds formed minus 5 times the 413 again. Because you got 5 carbon to hydrogen, 1, 2, 3, 4, 5. Plus 1 carbon to carbon single bond, which is 348. Do what? Oh, there's 2 of them. You're absolutely right. Okay? 1, 2. And then the carbon to nitrogen triple bond, 891. Now, 891s cancel, 5 times 413 cancel. So you end up with 614 minus 696. So that ends up equaling all right, so bonds broken minus bonds formed. As long as you have the Lewis dot structure, so sometimes in the AP problem, the part A is draw the Lewis dot structure. And then part B is gonna be given that, what's the, what is the bond energy, and they give you the bond energies. And we'll go through next week, we'll be doing some practice problems like those. Okay? Now, just real quickly, I just want to go through the last 2 pages of the notes. This is something we've already talked about. I just kind of want to highlight. Speaking of bond energy, let me go ahead. I'm not going to write anything, so I can pull this down. It's real important We talked about heating curves at the beginning of the unit. How much energy, all the Q's, Q melt, Q boil, Q heat, okay? This is kind of a discussion of all that. But note that when we're going from solid to liquid to gas, phase changes, are we breaking the covalent bonds? No. What bonds are we breaking? IMFs, the intermolecular forces, because it's still water. Water is, it's ice, it's H2O, liquid, it's H2O, steam, it's H2O. Okay? So, phase changes involve intermolecular IMFs, which you want to make sure that you're not going to include those in your bonds energy broken minus formed. It's not going to be anywhere in there because we're not breaking those type of bonds. Okay? So that just kind of goes then fusion, vaporization, sublimation. What is sublimation? Solid to a gas, okay? An input of energy to overcome the attractive forces between the particles. Notice we did not speak of breaking bonds. Okay, so again, it's just a stress that phase changes involve changes in IMFs, not bonds. Then just a definition of a vapor. I've given this to you before. A vapor is a substance that's normally a solid or a liquid, you know, but it's in the gaseous phase. Water vapor, alcohol vapor, gasoline vapor, things that are normally solid or liquid. And then we know this, we talked about this in great detail. The more polar, generally the stronger the attractive forces are going to be. So you might want to look over that. And then on this page, the last page, there's a total screw up on this. Okay, but this right here is supposed to be the whole, this, and it won't, it's a PDF, so it won't let me move it. This whole thing needs to be moved down, and it takes that whole heating curve that I did at the beginning of the unit, where we're heating it up, melting it, heating it up, boiling it, heating it up. Okay, so that's what graph is supposed to be right here. This whole thing's supposed to be shifted down somehow when it translated to PDF. It messed it up. So we just need to know. So there are just some good things to ponder, and the answers are all there. So questions about that type of heating curves. That's an important curve for you to understand. So these are good questions for you to be able to, so we use MCAT when there's a temperature change. We use mass times the heat of vaporization, heat of fusion when there's a phase change. Good kind of a review of all of the heating curve type problems that we did at the beginning of the unit. All right, so that really is all of chapter 5. We're going to be doing chapter 19 at the end of next week. Okay, chapter 19 is much more simple and straightforward than this one. But we'll put it all together with delta S and delta G and go from there. Again, a reminder, we're doing a lab on Monday and Tuesday. It'll be Tuesday for y'all. Those of you watching online, it's going to be Monday. Okay, it's going to be a Hess's Law lab. And so wear appropriate clothes and bring your lab manuals with you. Okay, make a note to yourself. Go ahead and stop it.